Scientific graphing. How to create a graph of scientific data that shows the data in the best way. Suppose we wanted to graph the data shown in the table below. Before we can graph the data we're given, we need to know a number of things. We need to know, number one, which variable goes on which axis. Unlike math graphs, where we always know that x goes on the horizontal axis and y on the vertical axis, it is not immediately clear which variable goes where. So we need to be able to determine which is which. Number two, what is the range of values we should have on each axis? On math graphs, we almost always start from the origin and go up from there. The range of the data is usually the same on the two axes. On a scientific graph, the range on each axis may be different, and each axis needs to be decided separately. Number three, what kind of scale should we use on each axis? Unlike math graphs, where the scale on each axis is usually the same, and usually one box equals one unit, the two scales do not need to be the same on a scientific graph, and they do not need to be one box equals one unit. We will need to choose the scale on each axis that shows the data best. In scientific graphing, we have two kinds of variables. The first kind we call an independent variable. The independent variable is the variable in the experiment that we control. That is, it is the thing we are manipulating in the experiment. The other type of variable is called a dependent variable. The dependent variable changes because of what we do to the independent variable. But how does one determine which variable is the one that has been manipulated? The answer is that we need to know how the experiment was done in order to reliably determine which is which. Listen to me read this statement describing the experiment that generated the data shown earlier, and see if you can tell which variable is the independent variable and which is the dependent variable. A rigid container had gas added to it while sitting on an electronic balance until a certain mass was read on the balance. The pressure of the gas was then recorded. Which variable did we manipulate? That is correct. We manipulated the mass. What changed as a result of that manipulation? That's correct. The pressure changed. So the mass is the independent variable, and the pressure is the dependent variable. On scientific graphs, the independent variable goes on the horizontal axis, and the dependent variable goes on the vertical axis. Now we know that the mass goes on the horizontal axis and the pressure on the vertical axis. But where do we put the axes? In a math graph, the axes are most often placed in the center of the page, because we want to be able to see the function in all four quadrants. However, in a scientific graph, the values we have measured are most often positive for both variables. So only one of the four quadrants has any data in it. As a result, the axes are most often placed on the left and bottom of the sheet, like this. In addition, we need to label the axes for a couple of related reasons. First, there are a lot of possible quantities we could be graphing, so we want the graph to show what those quantities are. And second, we need to be clear about which axis represents which of the two variables we are graphing. We need to indicate not only what we are measuring, but also the units we are using. So, on the horizontal axis, we put mass, grams. And on the vertical axis, pressure, kilopascals. What is the range of values we should have on each axis? The range of values on the axis identifies the smallest and largest values on the axis. On math graphs, we almost always start from the origin and go up from there. So the range will be from 0 to whatever the largest value is. However, if we start from 0, that may leave a large part of the graph without points. In the data we were given, the smallest mass is 255 grams, and the largest mass is 260 grams. So if we start at 0, our points will be clustered at the right edge of the graph, and it will be hard to see what the relationship is between the variables. So in general, we choose a range that has a smallest value a little smaller than the smallest value for that variable among our data points, and the largest value a little bigger than our largest value for the variable. In the case of the mass, our range should be from a little below 255 grams to a little above 260 grams. For pressure, the smallest value is 82.28 kilopascals, and the largest value is 164.56 kilopascals. So the range should be from a little below 82 to a little above 165. Note that the two axes have very different ranges, and that neither starts at 0. There are times when it makes sense to start at 0, but often it does not. We are not quite ready to put our numbers on each axis. We need to talk about the scales for each axis. The scale used on an axis tells us what amount each block of the graph represents. On a math graph, this is usually 1, but on a scientific graph, we want to spread the data out so that we can easily see the relationship between the variables. The scale on each axis should spread the range out so it extends over most of the page. For the mass, we want the range of 254 to 261 to spread out over the approximately 50 boxes on the horizontal axis. This means that we could have 7 boxes to each 1 gram and have the range of 7 grams all appear on the graph. For the pressure, we have from 80 kilopascals to 170 kilopascals, a 90 kilopascal range, to spread out over 39 boxes. If we have 1 box equals 3 kilopascals, then we will get the range of 90 kilopascals within 30 boxes. While this doesn't use the whole graph, it uses most of it and is a convenient scale. So the horizontal axis will have a scale where each 7 boxes measures 1 gram, and which has the numbering starting with 254 grams and going through 261. And the vertical axis has a scale with each box measuring 3 grams and the numbering starting at 80 kilopascals and going through 170. Now we can graph our data. Part of the reason we want to have the right range and scale can be seen in the data we have to graph. Note that we know the pressures to 2 decimal places in kilopascals, but our scale has 1 box equal to 3 kilopascals. It's very difficult to place that point that closely, and the more condensed the scale, the harder it becomes. The more spread out the scale, the easier it is to place the points on the graph, and the better we will be able to tell the relationship between the variables. So we place the points as closely to the spot as we can determine it. Let's start with the lowest value, 255 grams and 82.28 kilopascals. That point goes here. The point 257 grams, 115.20 kilopascals, goes here. 0.258 grams, 131.65 kilopascals, goes here. The 0.259 grams, 148.11 kilopascals, goes here. And finally, the 0.260 grams, 164.56 kilopascals, goes here. The final step is to find what the relationship is between the two variables, mass and pressure. If we look at the data as we have plotted it, it looks like the points are on a straight line. If that is the case, we can draw a best fit line through the data. The best fit line is the line that comes as close as possible to as many of the points as possible. It is a line in the mathematical sense and has an equation that corresponds to the general linear mathematical equation, y equals mx plus b. While there are mathematical ways to determine the best fit line, the simplest way to find it is simply to lay a ruler down on the graph and get it as close as you think is possible to the points on the graph. So the best fit line looks like this. Since the points seem to actually fall on a line, the relationship between the two variables is a line like this. Since the vertical axis is pressure and the horizontal axis is mass, the pressure corresponds to y and the mass corresponds to x. That means the best fit line is P equals m times capital M plus b, where P is the pressure, capital M is the mass, lowercase m is the slope, and b is the y-intercept.